Hey dudes, this should be a quick one. We're looking at the second and higher derivatives. It's 5/7 out of 15H in the text. And I know you were thinking that like calculus was the end and you take the derivative and that's it, but you can also keep going farther. Instead of just taking the first derivative, you can keep going and take the second derivative, f prime of x or y prime or d2y over dx squared. Sometimes the Brits use this as double dashed x, but I often hear about it as double prime. So here's Optimus Prime. Get it? So let's just look at an example of that. So here's your function. They're asking for the second derivative. So you take your function and let's rewrite this piece with an exponent, because then we can use the power rule on it. We multiply the 3 in the front and decrease the exponent by 1, and the same sort of thing for the second piece. The negative and the negative give you the positive, and then we decrease the exponent by 1 here. And perhaps we throw it back into perhaps we throw it back into fraction form if you were going to leave it, but they asked us for the second derivative. So just differentiate the first derivative and you get the second derivative. So we're going to multiply this in and decrease the exponent and then do the same here. So when we do that to this piece, we get 6x and x to the first, right? And this second portion, we get 6x. The negative and the positive make this negative, and we decrease the exponent again by 1. It's the same process, right? And then maybe, since we were given this fraction notation, clean it up. So turn this fraction into this piece. Cool. All right. So that's like taking the second derivative. And like, why on earth would you do that? Well, physics is a good one. If you need physics, some people don't, like this owl. Physics is the one that makes the most sense to me. Other applications in business and things like that. But here's an idea. If you throw an object up in the air at a certain speed from a certain height, you can model that using kinematic equations, right? You get like the displacement is 1/2 at squared plus v naught t plus initial distance, something to that effect, d naught. And if you plugged in your acceleration due to gravity and your initial velocity of 3 and your initial height of 10, you'd get this equation. I should probably do that in red, right? This equation describes the object's path as time goes on. So this would be like height and this would be time. And if you threw this straight up, it would go up from 10 up to a certain little maximum, wouldn't go too much higher than that, and then it would come back down, right? And that's this is, you could call this f of x. And that function would be the position, the height versus time. It's not moving in the x direction. If you take the derivative of this, right, you get this piece. You get negative 10 plus 3. You're taking the derivative of the top equation. It would give you this equation, and this equation is the velocity. Talking about how the velocity is changing. Because first it's going up, it has a positive velocity, then it stops, it has 0 velocity, and then it goes downhill, right? Here's where it has 0 velocity. It's right underneath where it stops and starts coming back down, right? It has to go up and then stop and come back down. So this curve, this line is the velocity curve. This f prime of x is how the velocity is changing. Starts positive, starts at 3 where you started throwing it up, goes to 0, which means it turns around and then starts coming back down. If you take the derivative of this, you just get negative 10, which is the acceleration. It's constant, and it's constant downward acceleration. If you're in physics, you're used to that. So this is f double prime of the original function. Cool. Sometimes you don't always have just a nice smooth curve like that. If you were looking at this in a different format, like maybe you were accelerating something, and this is displacement, right? This is displacement over time, and you were changing, it getting faster and faster and faster and faster, and then you you don't quite go as fast and you slow down a little bit. If you take the derivative of that, you get displacement over time, you get velocity. So this is the velocity curve. You can see our velocity increases, and then it holds constant, and then it decreases. That's where it holds constant. The displacement is changing linearly, right? So it's holding constant and then decreasing. So it takes us some time to get up to speed. We hold our speed, and then we drop off again. When you look at this portion from here to here, where we're having this quadratic style change in our displacement, those parts, you're getting this acceleration that is not zero. We accelerate, we have some acceleration. Here, no acceleration, right? And that's here. You can see that our no acceleration, so it means we keep our high velocity. And then here we decelerate, or negative acceleration, right? And you can see our velocity drop off. Acceleration is not always constant. So if we take the derivative of the velocity, we get the acceleration like we thought. But you can take, if you have a curve that describes the acceleration change, you can also take the derivative of that, and you get the third derivative, which is they call it the jerk. Think about being in an elevator, and like while you're moving up, while you're accelerating up, it's still constant. Or if you're being pushed back in your chair when your jet is taking off, you're feeling acceleration. You feel your back being pushed against that chair, but it's smooth, right? It's smooth acceleration. In this area, you get what's called a jerk when you have a changing acceleration. You see that this is not smooth. It's not a horizontal line, right? And this is the jerk. It's how much change in the acceleration you feel. Cool. So there's a lot of great physics jokes about that, like this. Here's displacement. Good day, displacement. Good day to you too. Here's velocity. Hi there, velocity. Hi. Right. Hi, acceleration. How you doing? Doing quite well yourself. Here's acceleration. Sure is a glorious day, isn't it? And it says, whatever. Jerk. Get it? He's being a jerk. All right, so you can take multiple derivatives, and sometimes they're meaningful, sometimes they're not, and sometimes they're worth like turning into a sketch and a joke. There you go. Don't be a jerk. Bye.